This is section 10.3a, ellipses. Let's review one more time the basic conics, because an ellipse is a conic section, and I know that by now you're probably getting used to seeing this, or perhaps even sick of seeing these images, but you know, repetition is the mother of learning, so we're going to go through it again. Conic sections are the shapes that are formed when a plane cuts through a double cone in different ways. Okay, so today we're going to learn about ellipses, which is the shape that you get when a plane cuts through one of the cones of a double cone at an angle. And you can see here that this plane is cutting through the bottom cone at an angle. And so we get an elliptical shape. We've already learned about parabolas, and circles you already learned about long ago. They're not part of this chapter. And then next section we're going to learn about hyperbolas. These are the elements of an ellipse, and it's very important that you copy this image down, and that you copy it down exactly. Because as you do these problems, you're going to need to keep referring to the image to keep all of the different elements of ellipses straight. So it's very important to copy this down accurately. And I'll explain the elements now. So let's talk about the definition of an ellipse. Remember that in this chapter we're defining shapes not by their equations, but by elements of the shape itself. Okay, we did that already with parabolas, where a point on a parabola, any point on a parabola, is equidistant from a focus and a directrix. Today we're going to do something a little bit different, where we have a distance, d1, from one focus to a point, and a distance d2 from another focus to a point. And d1 plus d2 equals a constant, and that constant is m, and m is the major axis. All right, so to read that definition, it would sound like this. An ellipse is a curve determined by the set of all points, the sum of whose distances from the foci is equal to the major axis. Now that definition may sound confusing to you, but graphically it's represented in this way, where I have d1 as a distance from one focus to a point, d2 a distance from the other focus to a point, d1 plus d2 equals m, and m is the major axis. It's called the major axis because, as you can see, an ellipse is an oval, which means that one axis will be longer than the other. You know, with a circle, each axis is equal, one's equal to the other, but with an oval, one axis will be longer than the other, and the axis that is longer is called the major axis. Now, what do these variables stand for? These labels, rather, they're not variables. V, if I look on the left, V is vertex, and the vertices of an ellipse, by definition, are the end points of the major axis. The end points of the major axis are the vertices. And so I can see V on the left and V on the right. This happens to be a horizontal ellipse. We're also going to learn about vertical ellipses. I've labeled the major axis M, capital M. The center is at coordinates HK. The foci are labeled with F, and of course D1 and D2, which added together equal M, the major axis. Now in the next screen we're going to kind of look at a demonstration of how D1 plus D2 equals M and how ellipses are traced. Okay, so this is to just illustrate how D1 plus D2 equals M, which is what we talked about on the last slides. All right, so these tacks represent the foci, and this string is going to represent D1 and D2. You'll see what I mean in a minute. All right, let's suppose that I've got a point on an ellipse. Looks like this. Well, D1 plus D2 equals M, the major axis. We're going to verify that it equals the major axis in just a bit. But the point of this first part of the demonstration is just to show that D1 plus D2 traces out an ellipse. Okay, so follow the pencil. I'm going to make a perfect ellipse. I'm just going to go up to that half. Okay, and then I'm going to come back down here, and you should be seeing how this relates to an ellipse, because what happens is the length of the string is constant, but D1 and D2 are changing. However, D1 plus D2 is still the same length of string, and so this traces out a perfect ellipse. Alright, so I did half an ellipse. Now we're going to do the other half. Just going to put it here where I left off. And we're going to trace out the ellipse again. And you can see how this is working, right? You see how this is working? The length of the string remains constant. D1 plus D2 equals the length of the string. And the foci determine the shape as we use them to trace out this ellipse. And there we have a perfect ellipse. Alright, we have a perfect ellipse. This is a horizontal ellipse because the major axis is the long one. And now I'm going to put the tacks in there again, just to show you where the foci were. So there are the foci. And notice, remember that D1 plus D2 is not only a constant, but it happens to equal M, which is the major axis. Now, if I go from knot to knot, the holes in the knots were centered on the thumbtacks. So the actual length of the major axis is that, and as I can see, that matches up perfectly with this ellipse. From knot to knot, that's the effective length of the string that I was using to trace this ellipse, and the knot to knot length is the same as the major axis. Well, that knot to knot length is M, and M is 2A, and that equals D1 plus D2. Okay, so hopefully that demonstration helped a little bit to visualize the defining characteristic of an ellipse, which is that D1 plus D2 equals M. Now you should look at these images and also copy them down accurately, because you will be referring both to these images and to the images earlier on in this lesson whenever you do problems, because you need to keep all the elements straight. The only challenging thing I think about problems with conics is that there are a lot of elements involved and you need to keep them straight. But you know, once you get used to them, and if you do take good notes, you should be fine. So these are the standard forms of the ellipse. On the left side of the screen we have standard form for a horizontal ellipse, and on the right we have the standard form for a vertical ellipse. Let's go through these elements. Right now I'm going to be looking at the horizontal ellipse. It's called horizontal because the major axis is horizontal. We have the HK, that's our center. We have the foci labeled with F. We have the vertices labeled with V. And what C is the distance from center to focus. Okay, that's very important for you to write down. C is the distance from center to focus. And over here, I'm labeling C as a distance only from the left focus to the center, but there is an equal distance of C from the center to the right focus. They're both C. Okay, so C is the distance from focus to center on an ellipse. I have my 2A, which is my major axis, and A by definition is half of the major axis. So, of course, 2 times A is M, the major axis. So 2a is the major axis, and this is a horizontal ellipse, so it's a horizontal major axis. And then also I have 2b equals little m. Little m is my minor axis. Little m is my minor axis. And b, by definition, is half of the minor axis. Half of the minor axis. So, of course, 2 times a half is the minor axis. 2 times b is little m, the minor axis. So then b is simply this distance from the center to one of the ends of the minor axis. Just as a is the distance from the center to one of the ends of the major axis. So you need to definitely copy this screen down. Copy down exactly. This will be an important part of your notes. Now the standard form for horizontal ellipse is up here in the upper left of the screen. I have x minus h squared over a squared plus y minus k squared over b squared equals 1. Okay, this is the standard form. And notice that a is going to be my bigger number, because if 2a is big M and 2b is little m, that's because a is half of my major axis. So if your bigger number is underneath your x coordinate, x being the horizontal axis, then you are dealing with a horizontal ellipse. On the contrary, and now we're going to jump over to the right side of this screen. On the contrary, if your smaller number is under your x coordinate and your bigger number is under your y coordinate, which is the vertical axis, then you're dealing with a vertical ellipse. So use whatever memory trick you need to keep that straight, but that's how to distinguish a vertical standard form from a horizontal standard form. Okay, continuing now, if I look at this right-hand side, I can see a vertical ellipse, and it's called vertical because the major axis, or the bigger of the two axes, the major axis is vertical, so it's a vertical ellipse. And the A's, B's, and C's mean exactly the same thing on a vertical ellipse as they do on a horizontal ellipse. So C is the distance from center to focus. A is 1/2 of the major axis. You can also think of it as the distance from the center to one of the endpoints, or one of the vertices of the major axis. And so 2a equals m. B is half of the minor axis, the shorter of the two axes, and you can think of it as the distance from the center to one of the endpoints of the minor axis. So 2b equals little m, the minor axis. I've got my vertices labeled. Vertices are the endpoints of the major axis. Got the foci indicated with F. HK is the center. And as I said already, the standard form for a vertical ellipse is x minus h squared over b squared plus y minus k squared over a squared equals 1. And notice again that your bigger number is going to be underneath your y coordinate, whereas with horizontal ellipses, the bigger number, the a squared, is going to be underneath your x coordinate. Okay, last but not least, very important, is what appears right here in the middle of the two images of these two kinds of ellipses. And that is what I'm circling right now with the mouse arrow. This identity, c squared equals a squared minus b squared. Okay, now we're not going to go through the derivation of that. It's actually just like the standard form for parabolas. It's just based on the distance formula. The distance formula in the Pythagorean theorem. And there is a proof in this in the book, and you can ask me about it in class if you want. But c squared is related to a squared and b squared in this way. For an ellipse, c squared equals a squared minus b squared. So c squared, or the distance from center to focus squared, equals a squared, or half the major axis squared, minus b squared, or half the minor axis squared. C squared equals a squared minus b squared relates all three ingredients of an ellipse. Now we're going to talk about finding the standard form for ellipses. In applications where you're trying to find the standard form, basically what you have to do is see what information you're given, and then use that information intelligently to find the information you're not given. All right, let's look at a specific example. We're going to find the standard form of the ellipse with foci at 0, 1 and 4, 1 and major axis of 6 units. Okay, remember that as you do these problems and also the classwork problems, you're going to make sure that you have good notes, complete notes, and you're going to be referring to the drawings a lot and looking at the elements on the diagram. So make sure that those are complete and accurate because those are going to be your friend for these next few sections. All right, so this is our first one, so I'm going to walk you through at least the first couple of steps. And as with parabolas, it's always best to sketch a rough graph. Okay, sketch a rough graph. And if we do that, we're going to graph the things that are given to us. So we know that 0, 1 is one of the foci. We also know that 4, 1 is another one of the foci. So we have a focus at 0, 1, another focus at 4, 1. We also know that the major axis is 6 units. So I can draw the major axis. And this has a length of 6. It just includes the 4 between the two foci and 1 on each side, so 6. And I know that it's centered because that's the nature of an ellipse. And the reason that we wanted to start with a rough graph is because this gives us a very important piece of information, and that is it tells us whether we're dealing with a horizontal ellipse or vertical ellipse. And since the major axis here is horizontal, then we are dealing with a horizontal ellipse. Now, you might ask, since this is our first time, how do we know the major axis goes through the foci? Well, major axes always go through the foci. And you can review the diagrams and prove to yourself that it's true, but that's just because the definition of a major axis is the longer of the two axes, and the foci are always on that longer of the two axes because that's how the shape is traced, such that d1 plus d2 equals m. And I'm talking about big M, the major axis. All right, so we've sketched what we can, and now we have to figure out the unknown. So this is a good time for you to pause, try to do as much of this as you can on your own, and resume if you get stuck. Okay, so we can just do a rough sketch of the ellipse, and we find that the center is 2, 1. All right, this is an important bit of information that we can get just from our graph. And how do we know it's 2, 1? Well, we know that the center is exactly halfway between the two foci. All right, and if that's true, then the only difference between the x-coordinate of the center and the x-coordinate of one of the foci is going to be 2, and that's why this is 0 plus 2, so 2. Or you could think of it as 4 minus 2, so 2. Well, 2, 1 is exactly halfway between 0, 1 and 4, 1. And that's simply because C, which is the distance from center to focus, C is the same whether we're talking about the left focus or the right focus. And if you have the same distance on either side of a point, then that point is halfway between the two endpoints. All right, so this is our center. And from our rough graph, we can fill in the following things that were unknown to us before. We know that A is 3 because by definition, little a is half of the major axis. And since the major axis is 6, half of 6 is 3. We also know that C is 2. Why do we know that C is 2? Because if my center is exactly at the center of the major axis, at the point 2, 1, well, then I know that the distance from that center to either focus is 2, and I can see that clearly here because the difference in x coordinates is 2. And I also know that HK is 2, 1. HK is our center. The center is at 2, 1. So the next step is to plug information into the horizontal standard form. We're using the horizontal standard form because this is a horizontal ellipse. X minus a squared over a squared plus y minus k squared over b squared equals 1. And now we just fill in what we can. We fill in what we can. And this is what we can fill in. So we knew that HK is 2, 1, so H is 2 and K is 1. We also knew that A was 3, so we put 3 in for A. And we don't know what B is yet, but we're going to find out soon what it is. Now, if for some reason you got stuck and had to resume to get help, this is another good time to stop. Try to get the rest of this on your own and resume if you get stuck again. Or if you did get the answer, then keep watching until you compare the answer you got with the correct answer. Okay, so to find B, we use that very important relationship that we saw in the diagrams. C squared equals A squared minus B squared. C squared equals A squared minus B squared. I can fill in my C, that's 2. I fill in my A, that's 3. And I need to find B squared, so now I just evaluate. 2 squared equals 3 squared minus B squared. Therefore 4 equals 9 minus B squared. Therefore negative 5 equals negative B squared, which is the same as saying 5 equals B squared. 5 equals B squared. And so now I can fill in 5 for B squared in the standard form, and my final answer is x minus 2 squared divided by 9 plus y minus 1 squared divided by 5 equals 1. This is the standard form for this horizontal ellipse, whose foci are at 0, 1, and 4, 1, and whose major axis is 6 units long. Let's look at another example. Sketch the ellipse given by 4x squared plus y squared plus 24x minus 4y plus 36 equals 0. All right, when you're given something like this, where the ellipse is written just as a polynomial, okay, this would be the polynomial form of an ellipse, 4x squared plus y squared plus 24x minus 4y plus 36 equals 0. All right, when you're given something in that form, you automatically have a signal that you should transform this into the standard form. Okay, so the strategy for this problem is first put this equation into standard form and then find the center, vertices, and foci. Now the problem itself tells you that it's an ellipse, so at least you know that. But we don't know whether it's horizontal or vertical yet. Okay, after we put it into standard form and find the center, vertices, and foci, we're going to sketch. All right, now putting it in standard form is going to involve completing the square. If you want the practice, then you should pause, try to complete the square on your own and transform. If you feel that you're still a little bit shaky on completing the square, then just keep watching and I'll walk you through completing the square. But again, it's always good to challenge yourself. If you think that you might be able to do it on your own, at least try it, because you know that whenever you get stuck, you can always just keep watching. So it is good to try to challenge yourself. All right, we're going to convert from polynomial form to standard form. And once we have standard form, we're going to know whether it's a horizontal or a vertical ellipse. So the first step was 4x squared plus y squared plus 24x minus 4y plus 36 equals 0. I simply rewrote the polynomial form. That's always a good step. Okay, then the next thing I did in this second line is grouped like terms, so I put the x's and y's together. And I moved the constant to the other side because that's going to get in our way for now. Next thing I do, and this is important, it's something you might be tempted to skip, but completing the square is hard enough already, so why not make it easier for yourself? A good thing to do is leave space. Leave space. All right, leaving space is a reminder that you have to add numbers in order to complete the square. All right, so let's go through what happened in this step. I took the 4 out, so we factored out the 4. and that's why this is just 4x squared plus 24x, but the 4 has been factored out. Okay, I didn't have to factor anything out here, so I just rewrote y squared minus 4y, but with parentheses. The space is our reminder. And then the negative 36 doesn't change. That remains the same. Okay, now the key part of completing the square is the next step. I need to add 9 to this first expression. Why? Because half of 6 is 3, and 3 squared is 9. Right? Half of 6 is 3, and 3 squared is 9. That's why I add 9 here. This is going to give me something that is a binomial squared. And then over here, half of 4 is 2, and therefore 2 squared is 4, and that's why I put 4 here. Okay, so when you're completing the square, you ask yourself, all right, what is half of whatever the middle term is? And then what is the square of that half? And that will tell you exactly what you should add. All right, now another important part of this step is what's happening on the right side. What's happening on the right side of this equation. Remember that from Algebra 1, you learned that whatever you do to one side of an equation, you have to do the other. All right, and so all we did here is we made up for on the right what we already did to the left. Okay, so what did we do on the left? Well, here we added 9, the number I'm circling right now with the mouse arrow. But notice that since the 4 was factored out, 4 times 9 is 36. So putting the 9 in parentheses here was actually the same as adding 36 to this whole left side of the equation. How do I balance that? Well, I add 36 to the right side of the equation. That's what this plus 36 is doing that I'm circling now. Okay, well, how about the 4? I added 4 here, and that's just a simple 4. You know, there's nothing factored out, so I don't have to multiply by anything. I added a 4 to the left side of the equation, therefore I add a 4 to the right side of the equation. Going on now, x squared plus 6s plus 9 can simply be written as x plus 3 squared, and y squared minus 4y plus 4 can be written as y minus 2 squared. So I'm almost done with completing the square. The last step is to divide every term by 4. Both sides of the equation by 4, and you end up with x plus 3 squared over 1 plus y minus 2 squared over 4 equals 1. And this is an ellipse. This is an ellipse. Now, you should be able to recognize, especially if you have your complete notes next to you, you should be able to recognize whether this is a horizontal ellipse or a vertical ellipse. Take a second to decide which one, and I'll give you a second just now to think about it. Is it horizontal or is it vertical? Is it horizontal or is it vertical? The correct answer is it's vertical. All right, it's vertical because with vertical ellipses, the a squared term, which is your bigger term, because that is, you know, half your major axis squared, that bigger term is going to be under your y coordinate, under the y variable, okay? And so this is a vertical ellipse. This is a vertical ellipse. What information can we extract now from this standard form? Let's do that systematically. We're going to extract it. Okay, now I know that some of you have watched without pausing because you wanted some help on completing the square. At this point, however, now that the square is completed, you really should be able to do the rest of this problem on your own. So pause the video, do it on your own, and resume once you have an actual sketch. A sketch that includes the vertices, center, and foci, and an ellipse that you've drawn. Okay, pause the video, do that now, and then resume. So here's the information that we can extract from our correct vertical standard form of this ellipse. A equals 2, how do we know that? Because A is going to be your bigger half axis, and A is the half of the major axis. 4 is the bigger number, so half of that must be A. A equals 2. Well, 1 is definitely going to be my half of my minor axis squared, and therefore the half of the minor axis that gets squared is just 1, because 1 squared equals 1. 1 squared equals 1. And therefore b equals 1. b equals 1. Now I know that c squared equals a squared minus b squared. So when I fill in 2 for a, 2 squared is 4, and 1 for b, 1 squared is 1, 4 minus 1 is 3, and therefore c equals root 3. c equals root 3. Filling in my a and b to find c. And finally, my hk is negative 3, 2, which I can get straight from the standard form, because x minus h, x minus negative 3, and y minus k, y minus 2. Negative 3, 2 is my center. Negative 3, 2 is my center. Drawing the sketch now, and since this problem asked for a sketch, and that's the main thing that it's looking for, well, here's where your sketch should be accurate. Okay, because that's the answer. You know, in other problems, maybe you're asked to find the vertex and the focus, or you're asked to find the standard form, whatever. You're not asked for a sketch, and therefore all you need is a rough sketch. However, if the problem asks you for a sketch, where a sketch is the final product, okay, that's where you need to be a little more concerned with accuracy. So that's why I'm labeling the grid here, labeling the x and y axis. And now we graph what we can. We know we can graph negative 3, 2. That's our center. We know we can graph negative 3, 0, because that is one of my vertices. Now, how do I know the coordinates? Because notice that negative 3, 2 and negative 3, 0 have the same x-coordinate, because this is a vertical ellipse. The major axis is vertical. The difference then is only in the y-coordinate. And since I know that a is 2, and a is half of the major axis, well, then there's a distance of 2 between these 2 points, because a is half the major axis. By the same reasoning then, the other vertex is negative 3, 4, because that would be a distance of 2 above the center. So I've got my vertices, and again, all I've done is just graph what I can gather from knowing a, b, and c. Negative 3, 2 plus root 3 is 1 focus, and negative 3, 2 minus root 3 is another focus. Okay, now let's take a look at this. We know that c, and I found what I'm circling right now on the far left, lower left of this screen, is c equals root 3. All right, we found that. And c is the distance from center to focus. So the y-coordinate then of the focus is given here in terms of the y-coordinate of the center. Okay, so this focus that's above is a distance of root 3 from negative 3, 2. And this distance that's below is a distance of root 3 below negative 3, 2. And the coordinates are then written as, for one focus, the one above, negative 3, 2 plus root 3. And for the other focus, the one below, negative 3, 2 minus root 3. Okay, at this point I am now ready to sketch. And this is what the sketch looks like, the ellipse. Okay, all we had to do was connect the vertices. That part was easy. We knew it was going to be vertical. And if there might be a remaining question in your mind, though, how do we know how skinny or fat to make this vertical ellipse? That's what B is for. Okay, so what I'm circling right now, far left, lower left portion of the screen, is B equals 1. B equals 1. Right, B equals 1 comes from the fact that the square root of 1 is 1. Okay, and B, referring now also to the diagrams, B is 1/2 the minor axis. The minor axis is the short axis, and therefore the width that I'm going to make this short axis is going to be a width of 2, because 2 is just 2 times 1. Okay, follow my mouse arrow now. All right, the mouse arrow right now is tracing the minor axis for you. Okay, right now I'm just going back and forth along the minor axis. Okay, from the center to one side of the ellipse is going to be a distance of 1, because B is 1. From the center to the other side of the ellipse is going to be 1, because B is 1. And 2B is my minor axis. 2 times 1 is 2, therefore my minor axis is 2. And that's why the width here of this vertical ellipse is 2 units. So this is the correct answer to the problem. Here's the classwork. Page 750, please write these numbers down. And in parentheses it says disregard eccentricity, because the directions ask you to give the eccentricity. I've chosen not to talk about that in this section, but I'll talk about it in the next section. So for now, simply disregard that part of the instructions when you're in class doing the classwork. If it asks you to find eccentricity, just disregard that. We'll cover it later.